I'm in my office. I wanted to solve a problem for you on the equations of motion. In this problem, we're thinking about a car and a van and a possible collision between the car and the van. So we're told that the car is traveling at 30 meters per second, and it's decelerating at 2 meters per second squared. We're told that the van is ahead of the car by 155 meters, and it's traveling at just 5 meters per second, and it's a constant speed. And we've got to figure out whether the car will strike the van, collide with the van, or whether the car will not hit or strike the van. And so that's the problem. And if the car does strike the van, collide with the van, we've got to figure out where, the location of the collision. So the first thing I did in this problem was list all the parameters, the quantities we were given. And so I've done that here. Upstairs, here's the information. Here's the data for the car. So in the problem, we're told, here's the initial location of the car. I'm going to just call it the origin. Here's the initial speed of the car. I've written it down here, it's 30 meters per second. And then here's the acceleration of the car. It's trying to slow down to avoid the collision. The acceleration is -2 meters per second squared. Because all of these refer to the car, this position X, this velocity V, this acceleration A, I put a little subscript on, it's S, on each of these terms. It's because the car was driven by Speedy Sue. For the van, the slow traveling van, I've written down the same information. Its initial position is 155 meters ahead of Speedy Sue. Its initial velocity is 5 meters per second. And the van is not changing its speed. It's traveling at constant speed. There's no acceleration. And so these are the corresponding information for the van. And again, to make it clear that this is the data, the information for the van, I put this little subscript V on for the slow van on each of these three terms. And so if I look back at this whiteboard right now, it's really a summary, a simple summary of the information or the data that we're given in the problem. And we've got to find out whether Speedy Sue collides with the slow van. Well, the way I did it was to take this information and write down an equation for Speedy Sue's position, location, as a function of time, and the slow van's position as a function of time. And then I'm going to see if Speedy Sue's position and the slow van's position coincide at a particular time. And if they coincide at a particular time, it means that they're in the same location at that time. It means that they've collided. So I want to write down two equations, one for Speedy Sue, which is going to be an equation for Speedy Sue's position as a function of time, and then another equation for the van's position as a function of time. And then we're going to use these equations to figure out if there's a collision, and if there is a collision, where is that collision? So let me write down first the equation for Speedy Sue. It's an equation of motion that the position at some later time is equal to the initial position plus the initial velocity times the time interval plus 1/2 of the acceleration times the square of the time. And all those initial positions, initial velocities, accelerations refer to speedy Sue. And I can just put in the numbers. Well, the initial position of speedy Sue is 0. The initial velocity is 30 meters per second, 30 times time, t. And the initial acceleration it's -2 meters per second squared. And so half of that is -1 meters per second squared. And so that'd be -1 times time squared. So this little equation here is pretty simple, actually, is speedy Sue's location as a function of time, 30t minus t squared. Let's do the same thing for the van. So for the van, again, we would use the same equation of motion. Too lazy to write it all out. But for the initial position, it's the initial position of the van. For the initial velocity, it's the initial velocity of the van. For the acceleration, it's the acceleration of the van. We put in those numbers rather than speedy Sue's numbers. So initial position is 155 meters. The initial velocity is 5 meters per second. So 5 times the time interval. And then the acceleration for the van, that's 0. And so this little equation here is the equation for the position of the van. Just to give you an idea of these two equations, let me just sketch them out. Sketch out speedy Sue's position versus time. Sketch out the van's position versus time. So here's the graph. Horizontally time, vertically position, and then on the graph of position versus time, position as a function of time, I've drawn two curves. One's labeled with an S for speedy Sue, one's labeled with a V for the slow van. Speedy Sue starts from the origin, and she's traveling fast and slowing down, and eventually she kept going, she would momentarily stop and then go in the opposite direction and speed up because she's undergoing constant acceleration. So when that constant acceleration is opposite her direction of motion, she slows down to a stop. When it's in the same direction as a direction of motion, she speeds up, getting faster. And this curve is actually called a parabola. And that curve that I've drawn is 30t minus t squared. That's what that parabola looks like. The van, here's the van's position as a function of time. It's actually a straight line. And it's a straight line because the van's not accelerating. The van starts at 155 meters from the origin and is moving slowly. So on the position versus time graph, this line is fairly shallow. And that line doesn't get any steeper or shallower because the van's not speeding up nor slowing down. So that's the position of the van versus time. And on this curve, this location here, that's the location where at that moment in time, the van and Speedy Sue are at the same position. And so that's the location where they collided. And we've got to figure out the time of that location and the position of that location. So let's see if we can do that. The way I'm going to do it is from the from the perspective that at this moment, Speedy Sue and the equation representing Speedy Sue's position and the van, they're at the same point, same place. And so I can equate these two equations at that moment in time to figure out the time of the collision. So let's do that. So at the point of the collision, Speedy Sue's position, which is given by this equation, is equal to the van's position, which is given by this equation. And if we solve this equation, we can solve it for the time, the unknown time in this equation. We can figure out the time of the collision. Then it'll be easy to figure out the location of the collision. To solve this equation for the time, we want to rewrite this equation. We're going to rewrite this equation as a quadratic equation. So if you look at the equation, it has in it time, it has in it time squared, and it has in a constant term. And that makes it a quadratic equation. And we're going to solve for the value of the variable, the time, in that quadratic equation. So if I rewrite the equation, I can rewrite it as t squared minus 25t plus 155 equals 0. And I did that just by moving these two terms over here on the left-hand side over to the right-hand side, leaving 0 on the left-hand side. So when I move the minus t squared over, I get a plus t squared. When I move the 30t over, that becomes a minus 30t, but there's already a 5t here. That's why I get the minus 25t. And then here's the 155. And so we have to solve this quadratic. So you probably met the sort of famous solution of a quadratic equation. If you have something like a times x squared plus b times x plus c equals 0. That's a quadratic equation. You can write the solution in terms of the a, the b, the c, the constants that multiply the quadratic term, the linear term, and the constant. I'm not going to go through the math of that now. I'm just going to write down the solution for you. If you're uncertain about the math of that, then that's described in, I would suggest you look it up in the textbook. It's described in the textbook, or look it up online, look it up in Wiki. But anyway, it's an equation that tells you the solutions. And the solutions are, and there's two of them when you have a quadratic equation in general. In this case, one of them is 10.2 seconds, and the other one is 14.7 seconds. And the 10.2 is this collision that occurs over here. And the 14.7, that's the second intersection of the two curves representing Speedy Sue's and the van's position as a function of time. So this is our answer for the time. This is when they collide at 10.2 seconds. And so that's the answer to the question, did they collide? Yes, they collided at 10.2 seconds. If you want to know the position at which they collided, now that's easy. To find the position at which they collided, well, that's the position of Speedy Sue at that time. And the position of Speedy Sue at that time is 30t minus t squared. And so all we've got to do now is fill in the particular time, 30 times 10.2 minus 10.2 squared. And if you calculate that position, that comes out to be 212 meters. And so the location of the collision is at 212 meters from the origin, 212 meters from where Speedy Sue started. And so if I go back up to this diagram, this time here of the collision, that was 10.2 seconds, we found that out. And this position of the collision, that's 212 meters. We found that out too. And so that's the solution to that problem. Now, I would say that that's quite a challenging problem involving equations of motion. The thing that makes it more challenging is that there's two moving objects. There's Speedy Sue in the car, described by equations of motion. And there's the van, slow van, described by equations of motion. And we had to solve the problem of when they collide, imagine both of those motions and imagine when the positions described by the equations of motion corresponded to the location of the collision. And that's how we solved the problem. And then we had to use some math. We actually had to solve a quadratic equation. And again, in physics, quadratic equations will come up. In physics, these equations that are describing or representing parabolas will come up. And so this problem is kind of a challenge problem, but it involves a lot of important ingredients that we will use time and time again throughout the semester.